Okay. Hello, everybody. This is Professor Ma, and this is the short introduction on the sections of implicit equations and implicit differentiations. And first, I want to remind you of this chain rule because we're going to use a lot of these. And specifically in our case, the letter U will be replaced by the letter Y. Okay, so remember that. For the algebra. So in general, we have two ways of producing graphs. One is giving a formula, the functions. This is called explicit because this is X is the input and the Y is the output. One input, one output. If I were to put in this form, we call that implicit. But because for one thing, it's not clear which ones is designated as the input, which one's designated as output. X, Y plays the same role. Okay, and you might say, well, there's no difference in this case. But in other cases, it does make a difference. This is the implicit form. And we all know this graph of this function is a circle. Specifically, the circles can be cut into two functions. The upper half is a functions, square root of 1 minus x squared, and the bottom half is square root of 1 minus x squared, including the endpoints. And so this is true in general that we can take implicit equations, cut them into pieces of functions. So here's another example. The implicit equation sine x equal to 0 basically breaks down into the only possibilities that this can be true. X, y is integral multiple of pi's. 0, 1 pi, plus minus 1 pi, plus minus 2 pi. So there are many equations. Any pairs of x and y product fit one of these equations is in the graph. So here's this graph. We have the coordinate axis. Actually, they represent x times y equal to 0. So that's the graph for x times y equal to 0. And for the purple lines, that's x times y is equal to pi. And the blue lines, x, y equal to minus pi. And so on, so on. So in this case, we have infinite many branches of hyperbolas goes out. We want to do the same thing in for functions. That's we want to find the derivative slopes. If I'm given a point, like here, that sits on the equation y to pi over x, I'm given the point at pi 1, and the question is, what's the equation of the tangent line? Now, of course, we can first say, let's solve for these equations, and starting from the very beginning, say, the point pi 1 sits on this specific equation pi over x. So we use that particular equation to take the derivatives and so on. Okay, but that's very laborious because we first have to locate where it is. And solve into a function form to take derivatives. That's not an easy task. This is a very simple functions, okay? And if I go down to some other function, which like, a very messy function or something like this, all the x's and y mixed up. This very difficult for me to solve for y equal to some functions in x, like pi over x here. So is there another way to do it? And the answer, yes, this is something we call implicit differentiation we can do. Okay. And to do that, okay, and let's start out with the implicit equation will be something in x, y over here on the left-hand side of some formulas, okay, and equal to some on the right-hand side formula x and y, okay. And the idea is we're going to take the derivative with respect to x, d dx. Okay, was it d dx both sides? Okay. In order for me to do this, let me start out with practice just how to do it on one side. And so like this type. Okay, suppose I have those formula, and what's the things I'm supposed to watch out. So right now that we're practicing just for simple expressions with x and y mixed. Now how do I take the derivatives? Okay, here the derivative is respect to x, and we say what's the y? Y, remember the chain rule? Y is treated as a formula in x. Okay, previously in chain rule we use a u of x. For example, if I'm talking about x cubed log of x, the derivative, okay, this is the product. Okay. We all know how to do this. This will be x cubed, or 3x squared times log x plus x cubed times derivative log of x with 1 over x. And what's different from here is instead of having log of x, I got something which y. And just think of that as log of x, a formula in x. So I retain the y here. Here, since I don't know what the derivative of y is, and so I write on that as y prime, dy dx, if you like. In fact, this is the part that I want, the tail part, which I want to solve for. Okay, so hence, a product rule, and derivative of 3x is 3x squared, y times y prime. What happens if I have the y cubed? Then the product rule says for derivative of y cubed, that's where the chain rule comes in. It's going to be yx to the third power. Okay, let me write like that. Okay, it's going to be 3 comes down y squared times the important part, the y prime. The part actually we want. Let me emphasize that. Okay. Here I put them together. Say, what's the derivative of these expressions? And in particular, I want you to, after you do these, notice in both expressions, there's a y prime sits in there. So I can collect everything with y prime for the algebra. Okay, and that's what it's asking. And see what a y prime is. And this is always very easy. That is, you collect everything that don't have y primes as one part, and everything with y primes as another group, and then take the y prime outside. And that's it. This is the basic algebra that we'll be doing. Okay. So let's do it for these equations. What? We're going to do it implicitly. So now we're going to take the y prime on both sides, the dx on both sides, and see how does this method works. Okay. Without solving for the equation y is equal to pi over x. Okay. Yeah, this is a way of avoiding all that. So we take the derivative of sine xy, and derivative of sine xy, of course, is cosine xy times derivative xy. The right hand side is 0. And so, and then I take derivative xy product rule. Remember the y prime that pops out, and so so we are aiming for what? We're aiming for y prime. Y prime dy dx. Right. Y prime is dy dx and dx, and this is roughly delta y delta x, and that's slope. And that's what. So we're aiming for that. And this is just a very convenient notation for tracking that. So these implicit differentiations. Now, for this equation to be true, this has to be true. Okay. I mean, and to solve for y prime, that's related to being 0. So that portion is 0. And then that says y prime has been minus y over x. Okay, here, I got it. I got a derivative of y. This is dy dx. You say, wait a minute, it doesn't look like the one before, like for functions. Of course not, because for functions, everything's in x, so the derivative will be everything is in x. Here, remember, we start out with an implicit mix x and y, so I wind up with a derivative that's in two variable, mix of x and y. But it's still usable. How? If I'm given the location of a point, here's pi 1, so all it says, stick the pi for x, put the y to be 1, and that's will give you the value. So once I have the slope, I can put into the slope, the point slope forms, and I get the equation. Okay, so then here is an example, how do we do these implicit differentiations algebraically. So for this one, for instance, I have no idea how to solve it. It's even possible. But I still want to know dy dx or y prime. So this is our chain rule from here out. A chain rule, product rule, quotient rule. First of all, this is a quotient, and when you use quotient rule, kind of messy. So at times maybe we want to multiply the denominator across. So use the product rule instead on the other side, instead of using the chain rule on the right hand side. So I multiply y squared across, so we use a product rule on that and differentiate both sides. Product rule, and this is a step-by-step they play out. Okay. And notice we got the y prime. It pops out. As we keep taking derivatives, and the y prime pops out at different places when we want to collect the y prime. Okay. So expanded. Okay, and so this is our algebra. And remember, after you collect the y prime, okay, let me divide exy first across to the other side. Okay, and then I want to collect the y prime, and here they are. And everything that's not to do, has nothing to do with y prime, that's on the other side. Okay, the other, on the right hand side, no y prime. Okay, that's all the junk goes to the other side. And the y, and then you extract the y prime, then you divide it by the coefficient functions. Okay, and that's it. Usually, when we get to this point, we can go back to the original formula, the relationship between x and y, like exy is equal to like y squared, something. Okay, so you can use these to simplify, and so if you want to play around with it, you can have a kind of nicer looking versions of things. Okay, but that's not required of the test unless the simplification is really easier. Here, e to x minus e to the xy cancels out. Okay. And oh yes, we then have another way to tackle the derivative of complicated looking functions is that we use the technique of log differentiation. So we started with the functions, okay, like this. Now, so now in this case, we started with a complicated has many components, multiply, divide, powers, okay. It has to be those kind of operations. Why? Because when we log it, it breaks into little pieces. So instead of finding the derivative of this using quotient rule, product rule, or go through all the chain rules, is we log both sides. In other words, this is now, if I interpret this as a implicit equations, I can try to find dy dx. Okay, you say, well, why? Because now the other side of the log that breaks apart into all these components which are easy to take derivative. Now I differentiate it on both sides using implicit differentiation. The log of y, derivative of that is y prime over y. And then on the other side, there are pieces of log. The derivative of that is u prime over u. So I got, bunch of simple sum of simpler terms for the derivative. Then I multiply the y across to the, or if I want to replace the original y, and that's the answers. Okay, so this is called log differentiation. And when do we use these methods? When the functions are built using exponentiation, multiply and divide. Okay. Yes, we use this for a function in those forms. Okay. The ones that can be easily broken up with the log. Okay, that's it. Have a good day. Bye-bye.